So, welcome again to class 2 of the material property course. So where we have stopped in the last class is we tried to just define formally define what material property is. We said there is a cause, there is an effect, and a response function that relates the cause and an effect. So is nothing but a property. Right. So that so that depends on what is the material. I mean, so material to material it may change, but the property is that of the material. Right. So cause doesn't belong to the material. Cause is something that I am forcing it to. I am inputting a forcing function, which is the cause. Right. So that's, let's say, gradient of temperature. That's, let's say, electric field. That's, let's say, voltage. That's, let's say, stress or strain. Whatever is something that I am forcing on the material. How the material responds and what I measure a displacement if I am applying stress, I measure a charge if I am applying electric field, or I measure a current if I am applying electric field. That is what I measure, right? But how the cause and the effect are related is up to the material, right? So that's a material property, right? So that's we will later on in this course we will actually look at this as what is called a response function, but for now we'll just call it a material property. Okay. So with that, let us try to actually, so since I am more interested in this course in trying to look at electronic, optical and mechanical, electromechanical properties, right? So let us give a brief. Let us start this class by giving a brief, overview of what are these. What is this capacitance? What is this? So electronic properties that I am talking about, right? So dielectric properties that I am talking about. Just I'll give you a brief background of so what is going to come next, right? So from then on I am going to assume that when I say polarization you understand what polarization is. Okay, so when I say charges you understand what charges is. Okay, so let us start this class by again going back to our favorite example of a parallel plate capacitor, right? So these are just two metallic plates. This is just people do this in physics 101 sort of courses. If you take a book like Griffith's electromagnetics, this is something very standard. So I have two parallel plates. These are parallel metallic plates, right? And there is nothing in between. So in between I just have vacuum, right? Then I apply voltage across these two parallel plates. So I am applying a voltage V, right? So or in some sense voltage V is nothing but so the electric field inside this parallel plate is nothing but V by D, where D is the distance between these parallel plates. Okay. Now the question is, how much charge or how much charge density am I putting on these, right? So if I apply voltage I am actually going to put in charges. That is what we said last time, right? So let charges be in a different color. So I am going to put positive charges here because I connected this to a positive terminal, and I am going to put negative charges here, right? So this is in vacuum, so there is absolutely no point of any sort of conduction, right? So all I am going to do is I am going to create charges and store them on these parallel plates by applying voltage. So I am storing energy in some sense. Okay. So how many charges am I putting if I just have vacuum, right? So as in between two parallel plates, that's the question, right? And that's quite an easy calculation to do. So we know that the number of charges that I put, or so that is given as the displacement vector, that is nothing but Q by A. A is nothing but the area of this parallel plate, right? So it is charge per unit area, right, is nothing but epsilon naught times E, where epsilon naught is your vacuum dielectric function, right? So vacuum dielectric constant, right? So even if I have no material, even if I have only vacuum, right? So the charges that I am putting on the parallel plate just inside vacuum is given as D equal to epsilon naught E, right? Okay. Now instead of having now let me do the same experiment, but instead of having two parallel plates and vacuum in between, I am going to bring in my material which is orange in color, right? This is my insulating material, or this is my dielectric. Okay. Now, the question is what will happen to the to the displacement charges. So, these are called displacement charges, which in vacuum are just epsilon naught E, but when I put in a material, what is going to happen, right. So, what so is it just going to be epsilon naught E, or are the number of charges on the plate that I have put increase, right. So, to answer that question, we need to understand what happens to the material first, right. So, the material inside a material. So, when I apply an electric field, right. So, the direction of electric field so will be this way, because this is positive voltage, this is negative voltage, right. So, the direction of electric field goes from positive away from the positive charges. So, the direction of electric field is this way, and when I have an electric field which is pointed in this direction, the material what the material does is the material polarizes. Okay, so let me, this is electric field, and the response of the material is that the material undergoes some sort of a polarization, right. So, there is going to be, when I apply an electric field on a material, the material polarizes. Now, what is polarizing? What is polarization? Now, so the question is, what is polarizing? Right. So, what is polarizing? It is nothing but the inside the material I am creating these little dipole moments. Now, what is a dipole moment P? From basic physics, we know that dipole moment is nothing but q times the so I have a positive and a negative charge, I separate them by a distance L, right. So, q times L is nothing but my dipole moment, right. So, this is the dipole moment. Right. So, I am creating these little dipole moments in the material which follow the direction of the electric field. So, I have applied an electric field in this direction, and I am creating these little dipole moments, and these dipole moments follow the electric field, right. So, in that sense, what I am doing to the material is I am actually trying to polarize the material in this direction. So, polarization in that manner is defined as P equal to the number of dipole moments, or sigma pi. So, these are all individual dipole moments per unit volume. So, this is the total dipole moment per unit volume. Okay. So, essentially what I am doing then is I am creating, so on these surfaces which are on the material. So, I am polarizing the material by applying an electric field, and on these surfaces I am actually creating, on this surface I am creating some positive charges. This dipole moment should end somewhere, right. So, if I have a polarization this way, I have a positive charge on this surface, these are what are called positive bound charges, and I have a negative charge on this surface. This is called a negative bound charge. Okay. So, this is what happens inside the material, right. Now, what am I doing to this material? So, I have now this dielectric material, and in the dielectric material I have put negative charges here, these are just bound charges, and some positive charges here, right. And then what I do is I have a parallel plate capacitor. So, I put a metal on the top and a metal on the bottom. So, this is a metal, this is a metal, right. And through a metal itself I have applied some electric field, right. So, this is the initial experiment to start with. Okay. So, alright. So, there are now because of these negative charges, right. So, because of these negative bound charges on the metal, what happens is to compensate for these charges so that there is no net electric field, the metal starts to induce some sort of a positive charge, right. Okay. So, these charges are being induced, these red charges, right. So, and here negative charges, right. So, red charges on the metal, the red colored charges on the metal are induced because of dielectric polarization. Okay. So, now so if I if I go back to my equation and then say how many total number of charges are there on the metallic plate, I am going to say that these are the total number of charges on the metallic plate. If I do not have any dielectric material, the total number of charges are just given by epsilon naught times E. But since I have now a dielectric material which is getting polarized, there are some polarization charges, right. So, that are these red colored charges are induced by polarization, right, because of the polarization of the material, right. So, D is hence epsilon naught E times P, right. Now, this P itself, which is how much the material has polarized, so this is again there is a cause and effect relation here, right. So, I apply an electric field and the material sort of polarizes, right. So, how much the material polarizes depends on how much electric field I apply, right. So, that is cause, this is the effect, but it also depends on an intrinsic material property, right, and that property is nothing but susceptibility. How susceptible is the material for getting polarized, or so it's separating its charges, right. So, there are let us say the positive charge, the center of positive charge and center of negative charge are smack on the top of each other. Initially there is no dipole moment or no polarization, right, and then I apply an electric field. So, I am going to separate them out. How much do I separate them out? How much dipole moment am I creating, right, depends on the susceptibility, how susceptible is the material to getting polarized, right. So, that is the definition of so that is what is polarization. Now, if my material is less susceptible, somewhat sort of softer material, right. So, polarization wise or dialectrically soft material, then it will polarize more. That means susceptibility is large, right. So, chi is large means my material is dielectric rather is a soft material, right. So, soft in dielectrically soft, not mechanically soft, but it is a dielectrically soft material, which means I apply a small field and I can generate large polarizations, right. So, or large dipole moments. If chi is small, my material is sort of it is a tough nut to crack, right. So, it is dielectrically hard material. Okay. So, here I have defined two quantities. One is what is called displacement charges. Displacement charges are the total charges on the metallic plates or charge density on the metallic plates, and one is the polarization charges. Polarization charges are these induced charges because I have a material that is getting polarized. Okay. So, these are polarization charges or charge density, and this is displacement charge density. Okay. So, now displacement, of course, now I can just write this equation plus chi epsilon naught E, and that is nothing but epsilon naught 1 plus chi times E, right. So, this is all again the assumption goes without saying is linear dielectrics. Okay. So, essentially what I also wrote my displacement as nothing but epsilon times E, epsilon being the dielectric function, right. So, epsilon is then nothing but epsilon naught times 1 plus chi times E, right, sorry 1 plus chi, there is no E, right, and this 1 plus chi, sorry, I will call this as epsilon r, or a relative dielectric constant, right. So, when I say my the dielectric constant of hafnium dioxide is 20, I mean the relative dielectric constant is 20, right. So, I am not giving the complete value of epsilon, rather I am giving just the dielectric constant, which means the relative dielectric constant of hafnium dioxide is 20. Okay. So, the dielectric constant of barium titanate is 200, which means it is the relative dielectric constant of barium titanate, which is 200, right. So, it is not and that is unitless, right. So, if you look carefully, the epsilon r is unitless, whereas epsilon itself has a unit of charge per field, right. So, charge density per field. Okay. Okay. So, effectively from this, right. So, we have defined two quantities, one is called the polarization, and polarization, when polarization is the response, I am just talking about the dielectric, right. So, dielectric gets polarized when I apply an electric field, and the amount of polarization it gets is related to susceptibility. So, susceptibility is the property of the material, right. So, this is the cause, this is the effect, and this is the property, right. And alternately, I can also say the displacement charges that I put on the metallic plates are nothing but epsilon times E, where epsilon is epsilon r, epsilon naught, let me write it that way, right. So, epsilon r is the dielectric constant of the material, right. So, and epsilon naught is just the vacuum dielectric of the material, and E is again the cause and D is the effect, right. So, these are the charges that I put on the plate, charge density that I put on the plate. This is how much additional charges in addition to the vacuum charges, right. So, the polarization the displacement has both vacuum charges as well as the polarization charges, right. Polarization charges are a part of the displacement charges. Okay. Okay. So, these are the two quantities, and if I sort of interchangeably use them, just so in the heart of the understanding, you should know that these are different quantities. Polarization is different from displacement. Okay. Okay. So, with that, so let us look at some of these other properties, right. So, I said so we also spoke a bit about what dissipative properties are. If I have a current that is flowing, if I have some flow that is happening because of force, those are dissipative properties. If I have some conservative properties, it is just equivalent to I do a charge separation, and then so that's it, I am not flowing any charges. Okay. Similarly, if I stretch a material, the elastic energy is stored in the spring, right. So, it is not being lost to friction, right. So, if the spring is moving around and there is constant loss of energy, then that is a dissipative process. But if I just stretch a spring, all the elastic energy is being stored in the spring, right. So, as long as spring extends only up to a certain extent, but if the spring starts flowing, if I apply a force, then there is some dissipation, right. So, that's called creep of materials or of spring, and so on and so forth, right. So, the properties can be dissipative, the properties can be conservative, but in general any property would relate cause and effect. Okay. Okay. So, with that, let us look at some of these so there are what are called conjugate quantities in thermodynamics, right. So, conjugate quantity of pressure is volume, conjugate quantity of temperature is entropy, or so I am just going to write it as enthalpy for now, right. So, these are related, but so conjugate quantity of entropy. So, if I change temperature of a material, the entropy automatically changes, or vice versa, if I change entropy of the material, the temperature automatically changes, right. So, they are intrinsically related with respect to each other. If I change pressure, if I apply pressure, of course, the volume should change, unless I do something else, right. So, but the basic idea is if I change pressure, the quantity that will change for sure is volume, right. So, unless I do some jugaad and try to not change the volume. Okay. If I change the electric field in the material, the charge, right. So, if I apply electric field, I am creating charge on the material. So, these are conjugate quantities, these are just thermodynamic, I am not going to do flow yet, right. So, again cause and effect. So, if E is the cause, D should be the effect, more or less, right. So, and E and D are sort of related by dielectric constant, right. So, V and P are related by the beta is the isothermal compressibility. T and S are related by Cp or Cp by T in some sense, right. So, SC ds is Cp by T dt, right. So, this is my property. Okay. E and D are related by epsilon, which is the dielectric constant. If I stretch a material, right. So, if I apply if I apply some force, or if I apply some stress on the material should strain, and stress and strain are related by what is called compliance, right. So, so x is S times capital X, and if I am straining the material, then so that is C times this is capital X, right. C is called the stiffness tensor or stiffness, and S is called compliance. Look how mechanical engineers, so S is the compliance and C is the stiffness, right. So that is so you have to match the following. It is so if you see S, I would have said S should be stiffness, right. So, but no, mechanical engineers thought differently for some reason. So, S is the compliance and C is the stiffness. Okay. All right. So, so these are all conjugate quantities, right. So, the properties that relate conjugate quantities are what are called direct properties, right. So there is no it does not so if I apply pressure, volume should change. There should be a property of the material that changes pressure, that changes volume with pressure, right. And so there is an obvious property that comes out of this. If I change temperature, entropy should change and heat capacity should take care of it, of the material, right. So these are the properties that relate conjugate quantities are what are called direct properties. Okay. So, this is just the definition. Okay. But imagine now that I apply stress, okay. I apply stress and I generate polarization in the material. How can I generate polarization in the material? That is here, right. So, D or P by applying electric field, right. So, if I apply electric field, I can polarize the material, right. But imagine that I have this beautiful material where I apply stress, this is stress, and I generate polarization, right. What is happening here? So, I am sort of not really coupling the conjugate properties, not really directly. Conjugate properties are anyway coupled. Here I am doing some cross coupling, right. So, I am applying a mechanical input and obtaining an electrical output, right. So, the property that relates the stress and the polarization. So, if I apply stress, can I generate some polarization? It is possible, right. So, this property is what is called the piezoelectric property. D, right, is the piezoelectric property. Okay. So, you apply stress and you generate polarization, or alternately so I change the temperature, right, of the material and I generate polarization. So, again I am cross coupling. So, these are all cross coupled properties. Piezoelectricity. Now, here what I am going to talk about is what is called if I change the polarization, if I change the temperature, the polarization typically reduces, right. So, that is because, okay, so I have a material which has some polarization. So, all these are dipole moments, right. So, when I heat it up, this material sort of starts to, because heat generates so the increase in temperature generates some sort of thermal disorder or thermal entropy, these polarizations start to disorder. Okay. So, the net P, right. So, these dipole moments start to disorder. So, the P actually here P1, and if I have P2 here, P2 is less than P1, right. So, I can change the polarization of the material delta P, right. So, by applying a temperature, right. So, how much did I change depends on a coefficient called pyroelectric coefficient, right. Here I am just applying temperature, it is thermal. What I am changing is I am changing an electrical property, I am changing the number of charges, I am changing the polarization charges just by heating up the material, right. So, piezoelectricity, you know, what is the other one, pyroelectricity, pyroelectric property. Then, you know, so when we talk about dissipation, we talk about what are called Seebeck coefficients, and, you know, thermoelectricity is the term that comes to mind. All these are what are called cross coupled properties. Okay. They take a cause from one domain, it can be mechanical, thermal, whatever, and they relate it to another domain, that can be electrical, magnetic, whatever, right. So, so piezoelectricity relates stress applied on the material with respect to the number of charges that I am creating on the material, right. For, I mean, stress and charge does not need to be related. If I can stress my material as much as possible and create no charge, that is perfectly okay, right. So, there are materials that where that happens, I can stress these materials and I do not need to create any charges, I do not need to polarize this material, right. So, that is perfectly okay, but you know, in some materials that happens, and so the mechanics of it is cross coupled with the the electrical properties, right. So, if I am going to call this a certain property, so this is a cross coupled property, but what sort of cross coupling is this? This is an electromechanical property, and that is the third part of the course. I said electrical, optical and electromechanical properties. So, we are going to talk a bit more about piezoelectricity, right. So, and how this is really you know, so piezoelectric is, you know, so piezoelectric materials are really useful for you know, making a lot of your microphone is, for example, works on principle of electromechanical actuation, right, and so on and so forth. So, so these are electromechanical properties, right. Pyroelectrics are, for example, you know, so I can make what are called infrared detectors using pyroelectric materials, because, you know, so if I have a pyroelectric material, I shine some infrared radiation, it will heat up the material and I can measure that heat as just charges. Charges are easy to measure, right. So, or charge flow is easy to measure in some sense, right. So, so I can, based on that, I can understand the you know, the IR radiation that is incident onto the material, right. So, so pyroelectrics, I mean, if you want to call it, you know, it is relating, so electrothermal properties these are, right. So, these are all cross coupled, right. So, I take cause from one domain and effect from another domain and cross couple it, and then there is a property that relates these two. It is possible that these properties are zeros, right, but you know, so in general for some materials these properties do exist. Okay, good. So, with that, you know, so we come to the conclusion of the basic you know, introduction of what property of the material is. Now, we will add in some more detail to this, right. Okay, so let us go back and you know, so you know, I was just using simple mathematical equations and saying that the property actually relates cause and effect, okay. But there is some structure to this property, right. So, I mean, there is some mathematical structure to what this property is, okay. So, for example, if I just change temperature, changing temperature is changing the enthalpy of the material is at constant pressure. So, changing temperature changes the enthalpy, okay. So, that is known, and how does it change enthalpy? It is through Cp, right. So, I said Cp is a property, okay. Now, okay, so temperature is a scalar quantity, delta H is also a scalar quantity, Cp, I mean, Cp does not have any particular directionality, Cp of the material is one constant property, right. So, Cp is a scalar property. It does not you know, so that there is no directional dependence of Cp, you know, Cp is different in different directions, all these things does not happen, okay. Similarly, you know, so if I take alpha delta t, right, and you know what I am, oh, okay, so not alpha will be a tensor, sorry. But if I take isothermal compressibility, right. So, if I look at change in volume, volumetric strain, right. So, this is a scalar quantity, this is just change in volume per unit volume, right. with respect to pressure, right. So, that is so there is a beta comes in there, a minus beta, right. So, isothermal compressibility is also a scalar property. Okay. So, these are, they do not have a particular dependence on direction, right, and you can see that temperature is a scalar quantity, delta H is a scalar quantity. If my input is scalar and if my output is scalar, if my cause is a scalar, effect is a scalar, the property that relates these two will also be a scalar property which does not have any particular directional dependence. Okay. Okay, so, these are simple scalars. Then what about vector properties which are vectors, right. So, properties can also be vectors. Which properties are vectors, right. So, that is an interesting question. So, if I change the temperature of the material and I induce some polarization by the way is a vector, right. So, so I can polarize the material in this direction or this direction or this direction. So, it has a directionality, it is dipole moment, right. So, dipole moment itself is a vector, right. So, P is Q R. So, to be very precise, I have to write dipole moment as not just Q times the distance, but Q times the displacement. So, it is Q R bar, right. So, it is a or sigma Q R. So, that is P. Okay. So, essentially P is a vector, right. So, P is a vector. Vector means it has components, it has an I, a j, a k component. So, I, P j, P k, right. So, as a result so I have what relates these two is what is called a pyroelectric coefficient. Pyroelectric coefficient also turns out to be a vector, right. So, pi j, pi k. It is not necessary that the amount of polarization I generate in x direction is exactly the same as amount of polarization I generate in y direction is the same as amount of polarization I generate in the z direction, right. So, pi is a property, but pi is also a vector, right. So, pi can be different in different directions essentially. So, pi 1, pi 2, pi 3, right. So, it can have 3 different components in 3 dimensions and so in general these need not be equal. Okay. So, pi is a vector quantity. Okay. Most importantly, right. So, you have so what are called tensor properties. Most properties are so okay. So, vectors are also tensors, scalars are tensors of order 0 of rank 0, vectors are tensors of rank 1, right. So, I will write here tensor of rank 1. Again we will define formally what a tensor is in the next class, but so from your basic background of from several other courses you sort of already get an intuition of what a tensor is, right. Now, so let us look at a second rank tensor. Second rank tensor means it has, I indicate it by 2 indices T I j, right. So, there are 2 different directions that are of importance in some sense, right. So, if I have a property which is let us say polarization, I am generating polarization in I direction, right, by applying an electric field in the j direction, right. So, what is the property that relates polarization to electric field? It is nothing but susceptibility, right. Now, susceptibility is a tensor, right. So, it has to relate the electric field in the j direction or in 2 direction with polarization in 1 direction, right. So, the susceptibility tensor component of the tensor that I will use here is Ij, right, sigma chi Ij times Ej, right. So, that is the polarization in the I direction. I am just looking at this component is equal to chi Ij times Ej, right. Now, in general I can have an electric field vector which is E1, E2, E3, right, and I want to see what polarization I am there will be a sigma here over j. I am explaining why that is the case. I will have to see so what sort of how does chi I j relate to E1, E2, E3, right. So, I can actually write P1 as chi 1 1 E 1 plus chi 1 2 E 2 plus chi 1 3 E 3, right. Or in general I can write a pi as chi I 1 E 1 plus chi I 2 E 2 plus chi I 3 E 3 or chi I j E j, sigma of chi I j E j with a summation over j. Okay. So, if I have these two indices, right, so I can so if so the so susceptibility is a property with two indices. So, susceptibility turns out to be a second rank tensor, and I am going to explain so why this is a second rank tensor, why these properties are tensors, right. So, we will have to define formally what a tensor is, but for today we will just take it as a tensor, right. So, it is a second rank tensor. And we will do some tensor algebra to actually understand a bit more about these properties, right. So, what does it mean that it is a second rank tensor? So, so first let me finish the notation. So, instead of, so in general pi is sigma chi I j E j, right. So, with a summation over j. Okay. Now, typically physicists are lazy people, so they do not, if it were me I would have written so P 1 equal to chi 1 1 E 1 plus chi 1 2 E 2 plus chi 1 3 E 3, right. So, the physicists come and say no, we would, or mathematicians, it does not matter, we would write this as chi I j so Pi is chi I j E j, okay, with a sigma. But then so we have some brilliant scientists such as Einstein who come and say, well, let us not even carry this sigma, right. So, let us just write it as chi I j E j with an understanding that if I have an index that is repeating, I sum over it, right. So, j is a repeating index. So, I sum over j, right. So, chi I j E j actually means this, right. So, it actually means chi I 1 E 1 plus chi I 2 E 2 plus chi I 3 E 3, okay. So, from now on I am just going to follow the genius Einstein and just write this, right, meaning to say that P 1 is actually given as chi 1 1 E 1 plus chi 1 2 E 2 plus chi 1 3 3, P 2 is given as chi 2 1 E 1 plus chi 2 2 E 2 plus chi 2 3 3 and so on and so forth. I sum over the repeating index is a repeating index that needs to be summed over. Okay. And such a notation is what is called Einstein notation. So, we will be using the Einstein notation from now on to actually look at how to deal with these complex, so how to deal with these higher order tensors, second rank, third rank tensors and so on and so forth. Okay. So, let me then summarize so before concluding this class, let me summarize what has happened. So, today we have actually built upon what we stopped in the last class, which is to look at cause and effect and look at properties as something that relates cause and effect, right. Now, cause can be in the cause and effect can be between two conjugate properties, right. And conjugate properties, there is nothing surprising because so if I change temperature by intuition, I have to change the entropy of a system. If I apply pressure by intuition, I have to change the volume, or vice versa. If I change the volume of the system by intuition, so I have to generate some pressure in the system, right. So, we have seen what properties relate, so the properties that relate the cause and effect which are conjugate to each other are direct properties, direct material properties, right. However, you can also have cause in one domain, effect in another domain, and there are properties that are relating these two. These are what are called cross coupled properties, and one of the examples of cross coupled properties is this piezoelectric property, right. So, which relates the stress that I am applying to the charge that I am generating, right. So, to the volt or polarization that I am generating, or pyroelectric property where I change the temperature of a material and then the polarization changes, right. So, the charges are changing depending on changing the temperature. Temperature is in thermal domain, whereas what I am changing is charges in the electrical domain. So, this is there is some sort of an electrothermal coupling in this material, right. So, that will couple these two things. Okay. So, we looked at coupled properties, And then we said, okay, now let us give a proper framework to actually look at these properties. It is not that, you know, so my material has one susceptibility, right. So, susceptibility, so these properties tend to be what are called tensors in general, right. So, there are simple properties which are just scalars or tensors of order of rank 0. And these properties are, you know, something like Cp, something like isothermal compressibility and so on and so forth, which have the same, or density of a material, for example, right. So, mass density of a material is a property which is a scalar, right. So, density does not change in different directions and so on and so forth. For a homogeneous material, I am assuming, so throughout this course I am going to assume that my materials are homogeneous. Material can be described by one property, okay. So, so density does not need to have any sort of directional dependence, right. So, density is a scalar quantity, that is the simpler property, but you have properties which are vectors that are dependent on the directions, right. And these vector, one of the vectors and probably the only one that I know of is this pyroelectric tensor, the pyroelectric vector, it is a tensor of rank 1. Right. So, we are actually going to formally define what tensors are in the next class, and then, you know, so the more complicated mathematics comes with second rank, third rank and higher rank tensors, and susceptibility is one such tensor, right. So, in the next class we are actually going to look at a bit of this tensor algebra to understand what tensors are really and how to deal with them, right. So, once we understand the language of it, then it becomes very clear, you know. So, you know, so how to deal with these properties which are more complex than what we think they are, okay. All right, thank you, and I will see you in the next class.